Okay, so we would like to explain how Euler came up with an infinite series, a power series actually, in powers of q, whose coefficients are exactly the numbers of partitions of the corresponding natural numbers. So the idea is as follows. We start with an infinite product of geometric series. The first geometric series has exponent, has ratio q. So it's q plus q squared plus q cubed and so on. The second has ratio q squared. So it will be q squared plus q to the fourth plus q to the sixth and so on. The third has quotient ratio q to the third. So it's q to the third times q to the sixth plus q to the ninth and so on. And we continue like this. So the next will have quotient, ratio q to the fourth, then we have one with ratio q to the fifth, and we keep going. And here we should say that we consider generically q to be less than 1 in absolute value, which means that if we multiply infinitely many of them, so here, the way that this product is computed is we have to think of an infinite distributive law, meaning we multiply, we take all products where they're infinite products and we choose one term from each parenthesis. And of course, there are going to be infinitely many such products. When we add them up, that will give us the sum of this series, and or that will give us this product. And what we need to understand here is that exactly because q is less than 1, if we have a product that has infinitely many powers of q in it, so let's say we go and choose, as an example, the second term from each parenthesis, and we multiply all this together, if we do so, we will get something that, if we consider its limit, because it's an infinite product, it will be 0. So every time we consider a product that has infinitely many of these q's, or powers of q for that matter, it's considered to be 0. The only things that eventually survive these brutal multiplications are the ones that for which we choose the number 1 from all parentheses, with the exception of finitely many parentheses where we might choose a power of q. All the others will become 0 and eventually do not contribute anything to the final sum. Again, here there's a slight leap of faith, and things should be explained through limits, but what we just said is actually a true statement. So if we put the limits down, so if we replace every infinite sum by a finite sum, and we make the computations that we just said, eventually everything checks out. Now, so that's the first step, to understand how this product is taken. The second step is to get a little deeper in the structure of this product, of what we're going to get. And for that reason, what we do, and this is, if you like, the big step, what I did already, it looks interesting, but it's meaningless as far as partitions are concerned. So the next step is to write all exponents in a very special way. So I will write this exponent as 1, and then q squared, I will write it as 1 plus 1. And q to the third, that will be 1 plus 1 plus 1 plus 1, and so on. And in the second parenthesis, I will write this as 1 plus q squared, and then 1 plus q to the 2 plus 2, and then q to the 2 plus 2 plus 2 plus 2, and keep going. And pretty much that's how we want to interpret all of these exponents. Why? Because we have this incredible thing. So let's say, for the sake of the argument, that and we need to make such a choice so as to understand what is going on. Let's consider the partitions of 3. Okay, so let's consider the partitions of 3. What are the partitions of 3? They're 1 plus 1 plus 1 plus 1, right? They are 1. Let me use different colors here, and you will see why I want to do something like that. So let me use green here and say 1 plus 2. And finally, let me use a red here and say 3. So consider these partitions of 3. Okay, and then ask yourselves how these partitions can come up from the products that you have. So for the first one, I can choose the q to the 1 plus 1 plus 1 plus 1. And then from all other parentheses, I will use the number 1. And when I multiply those things, I will get a q to the third. But more importantly, the exponent of that q to the third, I'm thinking of this as 1 plus 1 plus 1 plus, as 1 plus 1 plus 1. Then let's look at the second partition. That's a little more interesting, 1 plus 2. So now I will be choosing this term from the first parenthesis 1, and this term from the second parenthesis, and from all other parentheses, I will be choosing the term 1. As for the last one, I will choose, I hope you can see the pattern, from the first parenthesis 1, from the second parenthesis 1, and from the third parenthesis q to the third. And actually, these 3 ways that we have found are the only possible ways in which you can get, in the ultimate product, you can get q to the third. There's no other way. I mean, if you consider all other possible products, infinite products that contain the number 1 all but finitely many times, and you have other q powers elsewhere, there's no other way to get 3, which tells you that there's one-to-one correspondence to how many products you get where their ultimate power is 3 on the exponent of q, and partitions of 3, which somehow tells you that when you multiply everything out, and in some sense I'm singling out 3 here. So when I multiply everything out, first of all, you get the number 1 by multiplying all the 1s. Then for the moment being, I don't know what I'm getting in front of q, even though it's easy to find what I get in front of q. I don't know what I get in front of q squared, even though that is also easy to find. But with the analysis that I gave you, in front of q to the third, I'm going to get the number of partitions of 3. Okay, and then other things. And that's the interesting thing, that the analysis that I did with 3, I could have done it with any other number. And basically, we realize, or Euler realized, that what he gets in front of any power is exactly the number of partitions of that exponent. So in other words, this will be p of 1, this will be p of 2, and so on. And by the way, since we agreed that p of 0 is going to be 1, we also get this here. So in other words, eventually what turns out to be the case is this beautiful formula, which if for a second you consider that this was done in the 18th century you can understand that this was clearly a big leap for the time. So it's a formula that allows you, I'm not sure if it's so great for practical purposes, but it allows you to identify the partitions with something that you obtain in an analytic way. So Euler realized that this is P of 0 plus P of 1 times Q to the first plus P of square, so P of 2, meaning number of partitions of 2 times Q squared plus number of partitions of 3 times Q to the third plus number of partitions of 4 times Q to the fourth, and so on. And from the geometric formula, I mean, after all, this is a geometric series with ratio 1. Remember that calculus 2 tells us that this 1 over 1 minus q, this is 1 over 1 minus q squared, this is 1 over 1 minus q to the third. This is 1 over 1 minus q to the fourth. Eventually, what we get is this amazing formula. So the product, this denotes the infinite product from n equals 1 to infinity of 1 over 1 minus q to the n is equal to the sum from n equals 0 to infinity of p of n times q to the n. This is an incredible formula, and you can argue that this formula is really the ancestor of all Q series. Moreover, it's pretty much the formula that gave rise to all considerations about generating functions and so on. So this is an amazing piece of mathematics, and still you don't see where Euler is going with that, because you might say, okay, great, I mean, what can it give us? But remember that we already mentioned that there is a generic problem that to show that for each n, the number of partitions of n in odd components equals the number of partitions of n in distinct components. And you will see with this as starting point how Euler eventually solved the problem. So yeah, this is an amazing formula, and it's of vital importance in understanding how Q series work. Thanks for watching.